Okay, so our next speaker is Andreas Athenodorou, and he'll tell us about the confining string and the axion, a lesson from Lattice.
Thanks a lot, Ofer. I'm very happy to be here today. Thanks a lot for the invitation, and I'm really glad that that you managed such a success to get this all these important people together to work towards confinement. So what I'll be talking about today is the confining string and the axion, and what does the lattice teaches us, from all these years of work. So shall I remove this, maybe?
Yeah, if you can, on top. Yeah, there's 4 things at that one. Yeah, like
Okay,
this.
Great. So we all know that in QCD quarks are confined bound states called flux tubes. Okay, so long flux tubes behave pretty much like thin strings in the sense that if we pull the quark and anti-quark apart, the potential of the flux tube increases linearly with a separation with a coefficient given by the so-called by the string tension. So, however, if we keep pulling apart this flux tube, at some point will break, ending up, into separate flux tubes, and that's what we call string breaking. Of course, in order to have string breaking, we need to enable the vacuum to create a quark and an anti-quark. Okay. In terms of the lattice, this means that to include dynamical fermions in the simulation. So if we don't include dynamical fermions, we won't expect such a phenomenon. So since we are interested in the dynamics of the flux tubes, we work on the pure gauge and we forget completely about this kind of phenomenon. Okay. Now, as Sergey mentioned before, there are d-2 obvious massless Goldstone modes arising from the broken translation invariance in d-2 directions transverse to the flux tube, and therefore one would expect that there should be a low energy effective string theory model describing the energy spectrum of the flux tube. However, flux tube is an object that lives in SU3. It also has an intrinsic width, and therefore one could consider that there are also some other kind of excitations appearing on the spectrum of the flux tube. Now, how shall we investigate this scenario? Okay, so first of all, we use lattice to extract the spectrum of the flux tube. And once the spectrum is extracted, we can compare it with the theoretical description, which is the effective string theory prediction. And we check whether there is an agreement with the lattice data. Now, and if there is an agreement, then we move and we ask the question whether there is a lattice set of the lattice data, which is in a striking disagreement with the theoretical prediction. Okay, so this could lead us to some kind of massive excitations. Now, on the lattice, there are 2 different ways to investigate the dynamics of the flux tube. One is the well-known, open flux tube. Now, imagine that we have an open flux tube, with length equal to the length of the lattice. So we place it on the lattice and we compactify the lattice because we impose periodic boundary conditions. The quark will annihilate the anti-quark, and if the length of the flux tube is larger than the confining length, we will be left with a flux that wins around the spatial torus. Now, there's a lot of work going on the open flux tube by Gazelle, Bicudo, Brand, and also by Cudi. And there is also a lot of work going on the closed flux tube. Now, on the open flux tube, one has to also take into account that we have the boundaries, and therefore the boundaries will provide contributions to the spectrum. While on the closed flux tube, there are no boundaries, so we would focus just on the dynamics of the flux tube. However, the open flux tube is computationally not so expensive compared to the closed flux tube. And closed flux tube is really expensive because the length of the flux tube is equal to the length of the lattice. So if we want to extract the energy spectrum of the flux tube as a function of the separation of the length, we have to run many simulations. Okay, so for each different length, we need to run a different simulation. Actually, for this project that I had been working on for like a couple of years, I have run, let's say, 40, 50 different simulations. Okay, so it's really expensive. However, the closed flux tube has a far richer spectrum than the open flux tube due to the flux compactification. Okay, have the Kaluza-Klein modes. Now, as I said before, the flux tube lives in SU3. Therefore, we would expect like SU3 phenomena taking place, like global flux tube mixing. However, these phenomena cannot be captured by an effective string theory, and therefore one needs to suppress them, and the only way is to move to the larger limit. So actually what we do is that we investigate the closed flux tubes in the larger limit. Now, so far, these are the publications where we describe all that is I'm gonna present.
Do you mean mixing with an additional blue ball that gets emitted from the flux?
Yeah, exactly, yeah. So only this needs to be suppressed. I mean, for theories where, I mean, for let's say very low end theories, I mean, you see this kind of mixing. Now, as I mean, Sergey mentioned before, the most well-known description for the flux tube is the so-called Nambu-Goto. I mean, if we take the action and we perform a quantization, like quantization, we end up having this spectrum here, which is described by the winding number. So it tells us how many times the string winds around the torus. The longitudinal momentum in 2 pi q over L. The transverse momentum that we take to be equal to 0 because, I mean, it has nothing to provide in terms of physics. I mean, it's just the energy momentum dispersion relation and the total contributions of left and right moving phonons, which are connected, I mean, by the level matching constraint. Now, Nambu-Goto is Lorentz invariant in 26 dimensions. So there has been a lot of effort in trying to construct effective string theories, I mean, that are Lorentz invariant, and then we mainly have two, I mean, different approaches. Let's say, I would say the Lusher approach, where, I mean, Lusher introduced the Gaussian action in the static gauge, and then higher derivative terms, and the Pochitsky and Schrödinger action in the conformal gauge. Now, what this expansion basically gives is that we have the linear term, the 1 over L term, which is universal, the 1 over L to the power of 3 term, which is also universal, and the 1 over L to the power of 5 term, which has been extracted by Haroni and Karsten, which is universal for all excitations in three dimensions. However, it is universal only for the ground state in 4 dimensions. Now, this is nothing else actually, but the expansion of the relation I showed you before in units of 1 over L. So actually, what this tells us is that the leading order correction in Nambu-Goto would be actually, according to this expansion, would be actually of order 1 over L to the power of 7, which is something that we kind of see in our investigation. So I'm not going to mention, I will just say quickly that since Sergey, Rafael, and Victor published this paper, we could realize, I mean, this provided important information to understand that this additional state that we first observed like 10 years ago is actually corresponds to the axion. Now let me go to the lattice calculation and say a few things to understand better what we are dealing with. So we define the gauge theory on D cross 4 discretized periodic Euclidean space-time lattice, where we have the sides and the links, which are the basic elements of our gauge group. Now on the lattice, we calculate observables using correlation functions of color singlet objects, which are given by the path order product of links around closed loops. Okay. We use the standard Wilson action, where the basic degrees of freedom is the plaquette, which is the path order product of the simplest square one can construct on the lattice. And now energies can be calculated using correlation functions of specific operators encoding the right quantum numbers. So I would say that the keyword here is the right quantum numbers. So this is a pictorialization of a correlation function that corresponds to an operator, a Torellon operator, and a, let's say, anti-Torellon operator separated by temporal distance t. So the correlation function is given by this expression here. If we put two complete set of states, between the transfer matrix, we can show that this sum basically leads to the ground state as t goes to infinity. And we define the so-called effective energy, which basically leads to the ground energy as t goes to infinity. Now, this looks fine. I mean, these are examples of ground states extracted with this effective energy. However, what we are interested in is not just the ground state, but the excitation spectrum. So we need to use something more sophisticated. And this is called the variational technique, or the generalized eigenvalue problem. And according to this technique, what we have to do is to construct a large basis of operators. Okay, and these operators encode the right quantum numbers of the flux tube. Okay. So, and then we calculate the correlation matrix, which is given by this expression here as before. We diagonalize this matrix, extract eigenvectors, extract the correlator for each state, and then by fitting the results, we extract the energy for each state. So now let's see, what is the operator that would project onto a flux tube, a closed flux tube? The operator is basically the path order product of link matrices along the spatial direction. Now, since we impose periodic boundary conditions, this point is equal to this point actually. So this is basically winds around the torus. So it's this guy here, but we also have to sum over all different slices here in order to have a translation invariant object. So what are the quantum numbers that describe the flux tube? So we have the spin and the parity. Now, so then the way to give given quantum numbers is simple. Basically, we take the Polyakov loop, okay? We cut it and we put a wiggle, okay? And then we use, these Polyakov loops, okay, a linear combinations of these Polyakov loops to build operators that transform irreducibly with these three quantum numbers, which is the spin. This is an example of an operator that projects onto j equals 1. And we also have p parity and r parity. P parity describes reflections over the longitudinal plane. And this is an example of a reflection of, let's say, a transverse deformation on the flux tube, goes to something like this. And we also have parity transformations over the transverse plane. Okay, and this is an example of a transformation. Now, PR parity is a good quantum number when we are dealing with no momentum, because when we have momentum, there is no equal contribution of left and right moving phonons. Okay, so, and this is all the large basis of operators with transverse deformation that has been used in order to extract the spectrum. And as Sergey mentioned before, for instance, you can see we have the right quantum numbers here, also the right transverse deformations in order to project onto the axion. So in terms of the irreducible representations of the Gruber rotations, all the states are described by these 5 reducible representations times 2, which counts for R parity. So we have A1, which corresponds to spin equals 0 modulo 4, and P parity equals plus. A2 that corresponds to spin J equals 0, and P parity equals minus. E that corresponds to J equals 1 modulo 2. B1 that corresponds to J equals 2, P parity plus, and B2 that corresponds to J equals 2, and P parity equals minus. And these are examples of operators that project onto 0 plus plus, 0 plus minus, 0 minus plus, and 0 minus minus. So just to say that all these operators are actually built by hand. I mean, we hard, code these operators. I mean, there's no like a workflow which basically spits out an executable program. I mean, including these operators, and this is actually something that requires a lot of human effort. Okay, and this is the correlation matrix, which has this block diagonal form. Okay, so, and you can see that for each different reducible representation, we have the total number of operators used. Okay, for instance, for 0 plus plus, we use 190 operators. Okay, so let me say a few things about lattice, and then I hope I was not so boring. I will go directly to show you some results and make it more, let's say, interesting, the presentation. So what is the strategy? The strategy is the following. We fix the lattice spacing at 0.09 Fermis, and we move from SU3 to SU5 and SU6 by keeping lattice spacing fixed in order to see whether we can actually observe physics in the larger limit. So if SU3, SU5, SU6 give exactly the same result, we can ensure ourselves that what we actually get is the larger physics. And then we also move to a smaller lattice spacing, actually move to 2/3 of this lattice spacing, and we perform calculations for SU3 and SU5. Now, all these calculations that have been done for flux tubes that where the flux basically emanates from the fundamental representation of color. However, for K equals 2, for SU5, we have also investigated K equals 2 flux tubes. And actually some extremely interesting results came out of this calculation. Okay, so I guess since I've heard that a lot of effort will be given on the lattice calculations, let me just say a few things about what are like the constraints on the lattice. And I'll just say a few words about ways to mitigate, these constraints. So imagine that we are in n equals 3 and we want to move to n equals 6. This means that the time basically increases eight times, okay? And this is basically due to the fact that the matrix multiplications on a computer basically scale as n cubed. So in addition, if you want to go to a smaller lattice spacing, imagine that we want to go from lattice spacing A1 to A1 half. The calculation becomes 16 times slower because we have to scale up all the lengths on the lattice, all the extents. Okay, so it's already, these already show, some serious constraints regarding time. We really need lots of time, to perform detailed calculations on the lattice. And in addition to that, as we know, as we move to the continuum limit and as we move to the larger limit, we lose ergodicity. And this can be described as a topological freezing. The fact that the topological charge, because the different topological charge sectors are disconnected, basically, as we move to the continuum limit, the topological charge freezes. It doesn't fluctuate at all, and we get stuck at the same topological sector, and this means that we lose the ergodicity. Okay, so for instance, if we plot the correlation length as a function of a squared sigma, you can see that as we move to the continuum limit, this explodes as 1 over a to the power of 6 if we investigate SU3. Now, if we want to go to the larger limit, we keep the lattice spacing fixed, and we increase n. This increases exponentially. Okay, so I mean, this is already something that tells us that we cannot do much using this method, the periodic boundary conditions. For our calculation, I mean, we managed to go up to SU6. We had topological fluctuation. I mean, so it wouldn't make, let's say, it's not problematic in our case because I mean the topological charge would fluctuate. However, let's say we want to go to SU8 or SU10. I mean, there is no way that we can do that because the topological charge is frozen. However, we are scientists, so we are finding solutions. So, and there are solutions, okay? So, and the solutions, I mean, there are several ways to mitigate this problem. For instance, there is the so-called open boundary conditions where we impose Neumann boundaries on the time direction, which enables the topological charge to flow out of the lattice. And you can see here, I mean, the periodic boundary condition compared to the open boundary condition. This is like the evolution of the topological charge. You can see that with open boundary conditions, it's been fluctuating a lot. I mean, compared to periodic boundary condition, and this corresponds to SU7 at beta of 35, yeah. In addition, we also have recently the parallel tempering way of solving this problem. So basically what we do is that we put surfaces on our lattice and impose open boundary conditions on these surfaces. And this also enables, I mean, the topological charge to flow, I mean, in given sectors of the lattice. And this also makes things better. I mean, you can see that this is the heat path, the periodic boundary conditions, while this is the parallel tempering. And the advantage of this method than this here, because we have open boundary conditions, we have to alter the correlation functions. While here, we don't have to make any, I mean, any differences. I mean, we don't have to change anything. So also here, because of open boundary conditions, translation invariance is, let's say, does not occur anymore. So we need to keep away of the boundaries. Okay, so this is preferable, but I would really emphasize, and I mean, what has been going on in machine learning, especially, I really like this work. I think this is like one of the most exciting times in the machine learning contribution on the Lattice community, where they actually managed to use equivariant flow algorithms to improve the topological freezing. This is U1, of course. I mean, there is still, I mean, a lot of things to be done. I mean, we need to, I think, overcome also hardware, I mean, constraints, but I'm pretty sure that Fiala will give a very good presentation of this. So, and let's go and see some of the results. Okay, so I'll start with 2+1 dimensions. And what I show you here is, okay, is the energy in units of string or square root of string tension as a function of the length of the flux tube. So what we actually do here is that we extract the absolute ground state of the flux tube that corresponds to the ground state of parity plus and Q equals 0. We feed it with the ground state of Nambu-Goto, and once we feed it, we extract the string tension. And once the string tension is extracted, we can use Nambu-Goto as a parameter-free prediction for higher excitations. Okay. Now let's go to one step further up, and left equals and right. According to Nambu-Goto, this should be one-fold degenerate, and with Q equals 0, P equals plus, we go to the first excited state of P parity plus Q equals 0, and we extract the state that appears to become fully consistent with Nambu-Goto identity sigma of 3.5. And then if you go one step further up, and left equals and right equals 2, we have two states with positive parity, and these are the states that you see here. I mean, we get the right degeneracy, and this becomes fully consistent with Nambu-Godo at end root sigma of 4.5. And then the next state up, is in accordance with the right gap. So if we look at here, the first excitations in Nambu-Godo with negative parity will appear at this level here. So what we actually do is that we go to P parity equals minus, Q equals 0, and we extract the first excited state, the ground state, and the first excited state, and that's what we get. We get two states which are degenerate, and they are consistent with Nambu-Godo, and the next state up has the right gap. Now, if we go to okay, what I didn't mention is what happens to the absolute ground state in the correction terms. So what we actually do here is that we take the ground state and we fit the results with a correction term of 1 over L to the power of gamma. This is the chi-square per degree of freedom, and you can see that what this tells us is that the powers that lead to the smallest chi-square, this gamma equals 5 and gamma equals 7. Now, if we exclude gamma equals 5 due to the theoretical grounds, we can confirm that gamma equals 5 is actually in agreement with what Aharoni has extracted. Now let's go.
What happens when you extrapolate to below the value of L where E hits 0?
You mean below this point here? There is no data to do the extrapolation. I think this is, but also, well, here you approach also the criticality. So I would say that maybe different, different kind of phenomena will set in. Yeah. So, but this is certainly something that one can try. But as we move close to the criticality, the volume, in order to keep the systematics under control, basically explodes the lattice volume. Okay? So it is a challenge. Now, if we go to Q equals 1 negative parity, we get exactly the same picture. All states are in accordance with Nambu-Godo. The same happens for positive parity, Q equals 1, and the same happens for Q equals 2 negative parity and positive parity. So why I showed you these results? Because I want to demonstrate you that there is no any kind of other excitation apart from string-like excitations, as Sergei mentioned before. So now let's see what happens in 3+1. Of course, you already know. So let's go to basically it's the same game. So what I do is that I extract the absolute ground state that corresponds to 0 ++. I feed it with Nambu-Godo. I extract the string tension, and once string tension is extracted, I get a prediction for higher excitations. Now, if I fit these results here with a correction term of 1 over L to the power of gamma, okay, here you can see that the data that go closer to the criticality basically is the blue points, which corresponds to SU3 at beta of 6.338, and that's what I fit. And we get, this is the p-value of the fit. So it looks like it's more probable to have gamma of 5 and 7 as before. And due to the theoretical limitations, we can confirm that gamma equals 7 is actually the leading correction in this expansion. Okay, let's go to n left equals n right equals 1. So what I show you here is 0 ++, 2 ++, 2 -+. These are the states that cluster around Nambu-Godo, and they are consistent with Nambu-Godo. And then we also have this state 0 - that appears to deviate a lot from Nambu-Godo. Actually, it appears as the absolute ground state plus a constant term. So this was like the first sign that something strange is going on here. So it will be nice to see whether this changes in different ensembles. So what I show you here is results for SU3, SU5, and SU6, nothing, I mean, okay, there are some differences, of course, but I mean, qualitatively, nothing changes. I mean, what we actually see there is actually something that reflects to the larger physics of the theory. So what is really important here is that according to Nambu-Goto, there should be one state with 0 minus minus that should be consistent with n left equals and right equals 1. Okay, so if this state is not, then the next state further up should be consistent with n left equals and right equals 1. And you can see that the first excitation level of these quantum numbers of 0 minus minus doesn't appear to approach this line, but it appears to slowly approach this line here. Now, if this is actually the fit of Sergei approach, you can see that it describes our results very well with a mass of axion of 1.85. Now, if I subtract the absolute ground state, so what I do is I subtract the absolute ground state from this guy and this guy. This is what I get. I get a plateau for the ground state of 0 minus minus at 1.85. And the first excitation level appears to approach this line very slowly, okay? Now, it will be interesting to see, to see whether we also get hints or signals of other excitations, of other massive excitations within this, the flux tube spectrum. And actually, this is a case where this happens. So if we go to the second excited level of 0++ flux tube, what we actually see is something that behaves pretty much like the axion. Okay, this is for these four ensembles. So it is an absolute ground state plus a constant term. And so if I subtract the absolute ground state, what I actually get is a plateau at exactly twice the axion mass, 2 times 1.85. Okay, which I find really really amazing. I mean, of course, it looks like if it's like a bound state, the binding energy is negligible, but it looks like there is a relation between the two axioms here. And you can see that this is like the global mass, it's about the global mass. Now, let me go, I mean, and show you some results. For instance, for J equals 1+, we get 3 states that appear to be kind of consistent with the expectation of Nambu-Goto. And if I go to J equals 1-, I get something that looks like before, but the ground state and the first excited state appear to be degenerate and have, let's say, a massive excitation character. I mean, it's a ground state plus a constant term. And if I subtract the absolute ground state, I get something like this, which is still close to the axion mass. Okay, it's around between 3.10 and 4. So there are hints also of other massive excitations. Now, it will also be interesting to see what happens when we impose longitudinal momentum into the game. And this is an example of n left equals 2 and right equals n left equals 2 and right equals 1. Okay, where we expect to have like 7 states. You can see that some of these states, well, these states cluster around Nambu-Goto, but there is this state, which has, it corresponds to 0-. It has the right quantum numbers as the axion for Q equals 0, and it appears to have like large deviations from Nambu-Goto. By the way, this is like the ground state for Q equals 1, which is 1 for the degenerate. We get the right degeneracy. And I find this really also really important that we get this kind of agreement. Now, but let's focus on this state with the black dots. So what I show you here is the first excitation level, which appears to have, let's say, kind of similar behavior, but at some point, I mean, it starts to behave a bit, weirdly, in the sense that it looks like it kind of approaches this line here, but we cannot say much. So it could be that this state is slowly approaching this, and this corresponds to the axion. And if I compare this state to the axion with mass of 1.85 squared plus the momentum squared, added on the absolute ground state. So it's like a relativistic summation. We get a state which is in a good agreement with the axiom. And similar situation also occurs in Q equals 2, where the the ground state that corresponds to n left equals 2 and right equals 0 consists of these 4 states here. I mean, and these states cluster around Nambu-Goto. And the next excitation with 0 minus quantum numbers, I mean, doesn't appear to approach the next excitation level. However, it has these large deviations. And I mean, okay, if I do the same, let's say, naive hand-waving comparison, I get a state which, I mean, it looks like it behaves similarly with the axiom. So closing, I would just, I mean, closing the presentation on my results. I mean, there's only one thing left on the open flux tube, but it will be really quick. What I want to show you here is what happens if instead of having a flux tube in the fundamental representation, we have a flux tube in K equals 2 antisymmetric representation for SU5. So what I do is that I extract the K equals 1 fundamental and the K equals 2 antisymmetric representation. I extract the mass of the axion by subtracting from the ground state of 0 minus the absolute ground state. I feed this data here, I get this line here. And if I do the same for the K equals 2, I get this data here, which is in agreement with the mass of the axion. So it looks like also in the K equals 2 case, the mass of the axion is exactly the same. So it looks like this is a property of the worksheet. Now, finally, very recently, Pedro Vicudo, Cardoso, and Sharifian published a paper where they actually extract the excitation spectrum of the open flux tube, which is described by these quantum numbers that correspond to spin 0, spin 2, spin 1, spin 2, and so forth. Now, this corresponds to sigma G plus, which is like the most symmetric representation. J equals 0, positive parity, and also positive parity and charge conjugation along over reflections over this plane. So, and dashed lines correspond to Nambu-Goto or the RV exponential. And what we see here is that the low line, I mean, the first 4 states are Nambu-Goto-like. Okay, no signs of any kind of excitation of massive excitations. However, I mean, very recently in the Lattice conference, I realized that on their poster they had these 2 plots here for sigma G minus and sigma U minus, where I immediately realized that this state here appears to be behaving as a massive excitation. So according to Nambu-Goto, the first excitation of this representation, the ground state, should be consistent with n equals 4. Instead, they get this state here as a ground state. Okay, so if I subtract the absolute ground state, it looks like this approaches a plateau at with mass over root sigma of 2.3 approximately. However, if we go to sigma U minus, we get actually a tau. It looks like we get a tower of axions, and with no string states at all, string-like states, which is it's kind of fascinating. But if I do exactly the same thing for the absolute ground state here, if I subtract the absolute ground state here from this state, I get this, and this line is 1.85. So it looks like the axion on the worksheet appears also on the open flux tube. Of course, as I discussed before with Sergey, this was also already, I mean, one could also see that in older papers by Kuti. I mean, it was visible there as well. So I think the message is clear. So the flux tube looks pretty much like a bosonic string, even for short flux tubes. This is striking in 2+1 dimensions. However, it also holds for 3+1 albeit with some striking differences. So it looks like there is a massive axion particle with 0 minus minus quantum numbers on the worldsheet of the flux tube in 3+1 dimensions with this mass of 1.85 for SU3. Okay, this changes as you go to the larger limit slightly. It looks like there is a massive state with two axions with these quantum numbers 0++. The axion seems to appear in open flux tube as well. And there are also hints for more massive modes. So thanks a lot for your attention. Victor.
Could you go back to the slide where you had hints for more massive modes?
Yeah. Here.
Yes. So what are they? So there is one state which is we can call two axion states, which should be there.
Yeah. Well, I mean, okay. Look, I mean, these states. So we expect that n left equals 2 and right equals 2 corresponds. I mean, according to Nambu-Goto, consists of 3 states within which are described by the representation. So it's J equals 1 and J equals 3. Okay. So if I plot the 3 first states, I mean ground state, first excited state, and second excited state, I get this pattern here. So actually, if these were Nambu-Goto-like states, I mean they would approach this line here. But I don't know. They instead look like they are rising. They are. I mean, their mass increases. I mean, linearly with length.
I think it's important to clarify what Andreas means by massive mode. You don't need new massive field on the worldsheet. You mean like new, like non-Nambu-Goto state in the
Non-Nambu-Goto state. Yeah, exactly. That's what I mean. Yeah.
Bullshit particle like field in addition to axion. So
yeah,
it will be interesting to analyze for sure that state with 2 masses that looks like that what one expects for this two axion state. It would be interesting to analyze these other channels.
Yeah, exactly. Yeah.
Yeah, basically
that should be a simple
I was
state.
asking, can we explain those states with axion plus some goldstones, basically,
Right.
something like this.
I mean, if I understand correctly, this axion can decay into 2 Nambu-Goldstone particles, right? 2 massless particles. And can one see the fact that there is this mixing somehow in the?
I would say.
Well, that was this value of Q coupling which I showed on my plot. It basically shows up because you see this particle directly in the 0 minus minus channel, but then there is splitting between like 0 plus scale and spin 2 due to kind of axion exchange in the T channel, and that's probes that coupling. So
Is that something that has been calculated numerically?
Well, it's Q. I mean, Q is basically.
Yeah, so the value of the leading coupling, that's the duration. This is the width. The width of this particle. There's numerology there. The width of the axion extracted from the lattice.
Okay.
Corresponds to coupling, which would correspond to this integrable value of theory. That's exactly the piece of numerology. It has to do with that.
How well is that tested?
So how well it's been tested? We published a paper where we do the larger extrapolation for this.
Well, we estimated it's like 10%
For
there, which is we were trying to be conservative, but the main uncertainty there comes on the lattice side.
Yeah.
Due to splittings, because there is 2++.
Yeah.
Two polarizations of spin 2 states, which are supposed to be degenerate, but
So,
there's
yeah.
splitting between them, which is a lattice effect. So, and that's the moment that the limitation for.
So I think the splitting here would I mean, demonstrate, will provide the important information about.
But actually, that's what I was
Q.
going to ask. So, is there a way to improve the splitting between the two polarizations?
Yes, more statistics. No, it's feasible. Yeah, one can do that. But okay, what we need to do is
narrow this 10%
Yeah.
to 10% uncertainty.
yeah, we just need computational time. Yeah, but this is something that can be certainly done.
Are increasing the number of operators?
I don't think that increasing the number of operators will provide anything. I mean, new. Of course, this is something that actually needs to be tested. So now we're thinking of performing a calculation for global states, a systematic way to investigate whether, increasing, the increasing number of operators, reflects to the uncertainty. But this is not something that has not been studied like in a systematic way. But from my experience, I would say I don't expect much from increasing the number of operators. Of course, increasing the number of operators also causes some memory limitations, which in some cases cannot be resolved. It's a no-go.
Okay, so let's thank Andreas again.
Thanks a lot.